Please, the stage is yours.
Thank you. Thank you for being here today. Firstly, I will give more or less like the context of these objects here. Okay. If we have a subspace of our vector space, we can fix the things. So a subspace W in K2N, K is a field. We can extract the combinatorics of the subspace as a matrix. Okay, and that is our way back. If we represent a matrix over a field, so representation, okay, we recover a subspace of K2N. Okay, I will explain this in more detail today. But we can represent matrices over other algebraic structures. Okay, so if we represent it over the entropical numbers, we have a valuated matrix. That is basically the same thing as a tropical linear space. And we also have matrix over the sign hyperfield. That's, if you know about that, are in that matrix. Okay. Okay. And now what Baker-Bowler field does basically it extends representations of matrix over more general algebraic structures. That includes fields, the tropical hyperfield that recovers evaluated matrix, the sign hyperfield, and much more. Okay, and just to present some developments of this theory here, I can talk about flag vectors, flags, and observable tribes. And having based it on the tropical case by also okay. Well, tropical case recently made a drink, okay. And also based on the tropical version. That's Renzo. It includes also monolith space. Was developed by Baker and Warshide, and also based on the tropical version or inspired by the tropical version that are dresses. Okay, so if you know what a Coxeter matrix is, in this case of flags, we have a Coxeter matrix of like A, and here we have Coxeter matrix of like D. So it would be nice to find a theory of Coxeter matrix with coefficients also. Okay, so yeah, this is what's already done. And now I will more or less put the specific context of the work of what I will really present to you today. Okay, so let me erase that.
And the other one is better.
This one?
No, the right one.
Sorry.
Yeah.
So today, I basically want to include these objects, these matrix with coefficients, in a nice category. Okay, so I need some morphisms, and these morphisms are based on F1 linear strong maps of matrix. And with this, we will have a nice category.
So the previous framework of vector border, this wasn't the categories.
No, we have nice objects.
Okay, and then
Okay, and yeah, for here we have other types of objects here, and here we have a nice geometry, but now without a category yet. Okay. And well, whenever we have a category, we can study representations of quivers on it. So we have quiver representations, and with some geometry, we have quiver resonance. And again, this is inspired by the tropical case studied by Manoel Jarra and Victoria. Okay. And one more thing that happens in this setting is an application, basically, of this part here for nice quiver presentations over F1 lambda. This happens. Okay, so as an application of this construction, we can calculate, we can recover the Euler characteristic of this complex variety. So given a representation, an F1 representation of a quiver, lambda, we have a natural extension of this representation to a representation of over C, of C vector space, and we recover the Euler characteristic of this complex variety as F1 rational points of this quiver Grassmann in this sense, in this matrix sense. Okay, in a precise sense of F1 rational points. Okay, but my focus today is this, to present the category tree. Okay, so that was the overview. This story. Okay. So I don't know if everyone here knows what a matrix or what a matrix is. So I'll present it to you. So, matrix. Definition. Matrix. On a finite space. E is an unlimited collection of subsets of E. Okay. Such that whenever I have two of these subsets, and one element in one, but not on the other, can exchange this element here in a nice way. Here, I remove X from V1 and include Y. Okay? So whenever I have one element in one basis and not in the other, I can find another element on the second basis, but not on the first one, and exchange these two elements, and I have another two bases of my matrix. Okay?
And it's enough to consider only one of those conditions.
Yes, but for me, these two are nicer.
Yeah.
Yeah.
Not just for you.
Yeah. Okay. And matrices always come in pairs. So whenever I have a matrix on a set E, I have another matrix 2n, whose set of bases is just the complementary sets of bases of n. Specifically, this. This is the set of bases of another matrix on the same set E.
And I'm gonna have a follow-up question to
Sure.
Martin. So, okay, over say in the classical setup, so over the hybrid field, one of the relations is enough. Like if you're in the more general setting, do you actually need both of these?
No, it's enough because from having just this, we can prove that we have both.
Oh, I see.
Maybe with another Y. Okay,
But here you want them the same way.
yeah, but we can prove that.
No, but you have to change the y such that the first so the first b1 minus x plus y is still going to be a basis.
Yeah,
Yeah. Okay.
but yeah, I could put the definition of a matrix without this.
Yeah, sure.
Okay, but yeah, it works with all one.
Now the question was if in the more general setup you actually need both.
On the more general, it's a generalization of having both.
I see. Okay.
Okay,
even more
I will
general thing.
point out on at the moment.
Okay.
Okay, I have dual matrix. I have just a definition here of independent sets. So subsets of bases are independent. Okay, this is the name. And I want to present to you the circuits of the matrix. Minimal, a subset of P that's not independent, I will call dependent, and the minimal dependent that's I will call them circuits of them. Okay, just something. And there is a nice fact here. If I take a circuit of my matrix, a post circuit that's a circuit of the door, they satisfy this. It's not equal to 1. Okay? So whenever I have a circuit and a co-circuit, their intersection has or 0 or more than 1 element. I will call this property here, saying that C is perpendicular to D. Okay? Now, I will present to you how to get the combinatorics of a linear subspace. Yeah. So, you know, K, and this finite set here, 1, 2, and a matrix with entries in K. I will draw this as the columns C1, Cn, and n times n. Matrix. Okay, so n is the same n as here, and n is anything. There exists a matrix associated, matrix associated to this matrix here, given by this. Okay, so my independent sets of my matrix are the indices of sets of columns that are really linearly independent over K. With this, I have a unique matrix here, and this matrix does not depend on the choice of this matrix. It only depends on the row space of A. So if I have row space of A1 equals to the row space of A2, I have this equality here. So if I have a subspace of K to N, just construct a matrix with this subspace as the row space of the matrix, and I have associated to the subspace a matrix. Okay? Any questions about classical matrix here? Okay. Now I will enter on the coefficients. Well, here I have fields. I told you that over the tropical numbers, we also have a nice concept of matrix, but I will present a kind of algebraic structure that's generalized basically any kind of algebraic coefficients for a matrix that we had before. Okay. Medium. Okay. What's that? This one. A billion group. Okay. And F is the null set of F. This is a proper semi-ring ideal. And one more. There exists a -1. That's the idea here. Okay, so it's a group with a semi-ring playing the role of a null set here of sums that are 0, and there exists a -1. And morphisms of ADOs are what you would expect. So a morphism from an F1 to an F2 is just a morphism of groups that preserves loop sums. Okay. And let me show structure first. Yes, but I will show you right now some examples, some concrete examples of ideas. For example, notes. Notes K, I can associate this video here. Okay, where this right here are the formal sums in the same ring generated by this group here, such that the sum is really equals to 0 in K. Okay, so formal sums that when I calculate this sum in K is 0. Second example, the total field is this idiom here. As a group, just one, no signs. All natural numbers, but without one, and the -1 is equal to 1. And this guy here, that's the. Let's see what to the terminal objects in the category of fields. Okay.
Is zero a natural number?
Sorry? Yes, for me, yes.
Okay.
Okay. For example, maybe the most interesting for you that is about tropical geometry is the tropical hyperfield. Again, minus 1 is equal to 1.
So the morphisms also do that meet this mad epsilon to epsilon.
Yes, but I think that we can prove that.
Actually follows from this.
I think so, yeah. Because epsilon squares is equal to 1. Okay. And let me see. I'm not sure. I think that we can prove it in case better to include here. Okay. And just complete here. That's any other questions about these examples or about videos?
So hyperfield in my head is something like a field where the addition is multi-valued.
Exactly.
How does this fit to what you just told us?
Any hyperfield is basically 0 with a group, a 0 union group with a multiple rated sum. To view this hyperfield as an idiom, the group is the same. The null sets are the formal sums whose hypersum contains 0. That's it. Okay.
And
so
how
we
do you
can
go from an idiom to a hyperfield?
It's not clear because we have more idioms than hyperfields.
Oh, I see. So what you're saying with these examples is like we have the Krasner hyperfield, we have the tropical hyperfield, and we have an associated idiom for that.
Yes.
Okay.
Exactly. But if you have, for example, a partial field that's not a hyperfield, we can view partial fields also as idioms.
I see. Okay.
But yeah, we have more than hyperfields. Okay. So we know what a matrix is. We know what are the coefficients today, and I will merge those two now. Matrix with coefficients. Rational coefficients. Oh. Here, E is my finite set of before, and this R is just a finite number. Okay, just a natural number. It's a non-zero. Alternative, yeah. Let's find these equations here. First right and then exclude. And this is the dry definition of a matrix over an EDY. It's just an alternating with respect to epsilon being -1. So we have a row of switching entries here and appearing assigned. It's non-zero, and the most important part is it satisfies these equations here for any choice of r-1 elements and r+1 elements of P. It's more or less like the equations defining a gross volume or the quadratic equations that the determinants satisfy. Okay. And first example.
And what is F star class?
Sorry?
F star class?
It's, well, F star is a group, okay? Here we have the group acts naturally here. And an F star is just like the class of the natural action of the group on functions from here to here.
Saying if you scale such phi, then it remains a Grassmann function.
Sorry?
If you scale such a phi by an element of epsilons, it remains a Grassmann.
It's a Grassmann function, and I want that the matrix will be exactly the same. It's more or less like yeah, but the idea is the matrix is like a point on the projective space. Okay, so if you scale it, it's the same point. Okay. Even I'll make this that class function here. I have a real matrix associated with it. So coming back to your question, as before, if you look to these equations here, you will be able to recognize that here, in fact, it means, okay, the null set of the crosser is 0 and more than one element, so 2 or more. Okay. For such a sum being 0, or that is being on the null set of the crosser, or everyone here is 0. Okay. Or if I have one summand that's not 0, I have another one that's not 0. Okay. Here, the idea is like, or with this choice of elements x and y, or I don't have any basis for my matrix, or if I have one basis here and another basis here, I can switch one element here. Basically, I'm switching xk with yk with yr plus 1. Okay, and I recover the symmetric basis exchange axiom, or the strong form there. So that's why I really care about that form and not the simplest form. Okay. And yeah, for the crosser field, I recover all the classical matrix. So this theory really increases my matrix stuff. Okay.
And so for oriented matroids, you get chirotopes or the same thing.
Oriented matrices are in projection with matrix over the sign hyperfields. Okay. I am not sure about the chirotopes. Maybe they are the co-circuits in the sense that I will talk to you like to tell the story before. For any F matrix, I have a set of circuits and co-circuits and vectors and convectors. Maybe the chirotopes are one of these sets. Okay, so given an oriented matrix, I have the chirotopes. I'm not sure if are circuits or co-circuits, or if it's really the Grasman-Blocker function.
That's just the function.
The function. Okay, so yeah, I recover that. Yeah. But yes, for oriented matrix, they are included on this star here. And also for I'm not writing, but for states are in bijection with the tropical hyperfield right now. Okay. And now another example, maybe the most important one. That's
So this equation which is written, so in the case that everything are just vectors, say in Rn, is it then just saying something like this Cauchy-Linné formula for subdeterminants? So somehow this phi of x1 to x bar being non-zero means that you have some non-degenerate determinant, and then this exchange rule here, I think it's precisely this Cauchy-Linné.
I don't know precisely the equation that we are talking about, but the example that I will put right now is relating matrices to this star here. Basically, given a matrix, I will give you a Grasman-Blocker function. Okay, maybe this will be clear too.
I think the Cauchy-Linné is a little bit finer than this actually. And this is really sort of the Blocker function that defines a point cross model. Yeah, and Cauchy-Linné tells you not just about the subspace, but really the minor that we're talking about. So I think this might be related, but a bit finer than what we use in here.
Hmm. W here space picture. From R now every matrix R times N. W. So pick a basis of W, put on the rows of the matrix A. Write A as this. And this function here. Okay. Even a subspace with a choice, I have a Grasshopper function. And this association here is a rejection. I don't know if this example right now makes it clear for you. Yeah. Okay. Any questions? No. So I present to you a framework that recovers. What to say? This is basically the vector vector of the subspace here. But yeah, it basically recovers other kind of matrix with more algebraic structure. With some the idea here is to recover more or less the equations that define the subspace and the elements of the subspace. Okay. So for everything purpose, I can define the product. As a problem, we got problem with this, and I will say that the micro if this function is a no element, is 0. Okay. And now, given an F matrix, which is a class of a Grasshopper function, we explicitly two families. Ripples. That's this. So here, basically, we put some elements, some coefficients on the circuits and on the co-circuits of the classical matrix associated to this matrix with coefficient. Okay. These two sets are orthogonal in this sense, and they are closed by multiplication, by scalar multiplication. So if I have C, then B, okay. So, and if I have any circuits or co-circuits, the scalar multiple of this guy is again a circuit or a co-circuit. The idea is this family here are the defining equations of my linear subspace, and this family here are the elements of my linear subspace with minimal support. Okay, this is what happens in the case of field. And now, just some names. The vectors of R, basically the co-circuits. Okay. So if I have a family, I have a perpendicular family associated. Okay, the guys that are perpendicular to any elements of this family, and co-circuits. Say, and perfect. For any matrix, I will say that my coefficient set F is perfect if for any matrix this happens. This happens, for example, in the case of fields and the Krasner and the tropical hyperfields. But there are some ideas that are not perfect. Okay, for example, the phase hyperfield, if you know what this is. Is the real tropical hyperfield perfect? Real tropical hyperfield. I don't know. I want to say yes, but for a bad reason. It's because the simplest example that I know is the phase hyperfield, and you need the complex numbers. So, yeah, but the correct answer is I don't know.
Why does this condition matter? Like,
because with this we have nice morphisms.
okay.
We have composable morphisms. That's it. Let's start with an important example. And this happens here. Four vectors of M is exactly W. So from a subspace, we keep the K matrix associated to it, calculates the covector set, and it gives us again W. So here we have a bijection between subspace and K matrix. Okay. This is how we will recover.
Okay. Yeah. Yeah, James Maxwell is saying that the signed or real hyperfield is perfect as it is.
The signed
stringent.
hyperfield, yes.
Signed and real tropical hyperfields are both perfect as they are both stringent. Thank you.
Nice. So it answers.
Okay.
Thank you. Perfect. Now, literally, it's perfect. Yeah. If you know what a strong map of classical matrix is, you know that matrix with strong maps form a category. Okay. What's not so nice about this category is if we have a strong map from a matrix to another matrix, we not always have a induced map, strong map from the duals in the opposite direction. Okay. And I represent a smaller set of strong maps that has this property, this good property related to duality. Okay. So in classical matrix on a set S and the same on a set P. That's one strong map. And is which base points on my set S and on my set T also, such that so a next one linear strong map between this true matrix is it's pointed map between these pointed sets. Okay. And these two properties here. F the perimeter of T goes from the perimeter of T into the injection. This is the F1 linearity here. Okay, so the idea is I have a subset of this pointed set that goes through 0, including the base point 0, and another part that goes as an injection to T outside the kernel. And here is the part of the strong one. On that sense that intersection of two subsets or has 0 or has more than one element. Okay, this is an F1 linear strong map. F1 linear here, strong map. But
Okay, I mean,
yes,
it's not clear how this relates to strong maps of matrices from that definition.
it's because we have a lot of different characterizations of strong maps.
Okay.
One of those is this map here sends circuits through union of circuits.
I see, okay.
Okay, and the perpendicular sets here is union of circuits.
I see, okay.
Okay, so that's the relation to classical strong maps. Every F1 linear strong map is a strong map. But
Weaker than strong maps?
sorry,
It's a bit weaker than strong maps.
we don't have every strong maps, and the specific part of the specific subset of strong maps that are not included here are those that collapses parallel edges, because when we collapse parallel edges, we have two elements here going to T, not to 0, but they go to the same element. So it's not F1 linear. Besides that, yeah, every strong map is included here. So we have, for example, inclusions of restrictions of a matrix on the bigger matrix, contractions from the matrix should the contract that matrix is there, quotients are there. So basically, in strong map that does not collapse parallel X. And that's it. And go to and go. The whole start here. If F is an F1 linear map, forgot the strong part here, we have this from T underline to S underline. Basically, if an element of if an element of T is not on the image, put it going to 0. If it's on the image of F, send it to the unique pre-image here. And the fact is, if we had a strong map before, now we have a strong map. Okay, so with this, we have a category of matrix with morphisms as this kind of strong maps that has a contravariant involution on the category. So it's more or less like the category of vector space with duals. In fact, it's more like the subspace with perpendiculars. Okay. Now I will put coefficients on the F1 linear strong maps. Any questions for this combinatorial part? What do you get for fields? You mean what is the matrix defined over field? If your ideal is a field. What I will get is basically the objects are sub-vector space of a vector space with fixed basis. Maps are basically maps between the bases.
Like projection maps or inclusions.
F1 linear maps between the sets of bases.
How between the set of bases?
Okay. And it sends this. Okay. Given the F1 linear map, I have an induced linear map between the vector space, and it is a morphism in this sense if it sends the first subspace to the second subspace, or the other way around, depending on how you see. Okay, so it's basically maps between bases sets that respects the sub-vector space, the linear space there. Now the plus coefficients part. Now I want F perfect. Again, now matrix on finite set S and same on finite set T. Definition. One person from N to N. Matrix is a matrix. Matrix indexed by this set here, T times S, with entries in F, and here I want this set 0, 0, 0 again. Okay. Like that. 1. It's mononomial, which means row and column has at most one, 0 entry. The idea is this matrix is submonomial. It sends bases of F to S to bases, not to bases, but to a subset of base of this guy. Okay, and we can multiply by a star also. We can deform the elements of the bases, but we don't want like 1, 1, 2, 1, 2, 2. We want this.
So do you need that every row has at most 1, 0, 0 entry, or every row and color?
I want column also to have the one.
Oh, okay.
Okay. And yes. So whenever I have this kind of matrix too, I can multiply to a vector and I can multiply this kind of matrix with a tuple and get again a tuple here. Let me see here. So I want this. And okay, and the facts. Okay, these are composable if I have a morphism here and another morphism from P to N. Then here will be basically this and this. And this is again submonomial. And will be a morphism from P to N. So I have a category here of matrix coefficients, and if phi is a morphism from N to M, the transpose is a morphism between the duals. So again, I have a category, a nice category with the objects that I want, with a contravariant evolution on it. And how much time do I have?
-5 minutes.
-5, okay. So I just want to say that I have a characterization of morphisms with equations, as I have a characterization of matroids as pairs of circuits across circuits, and also as the definition that I gave to you as class of rational functions. Okay, so yeah, that's it.